Hello everyone, my name is Gaurav and today we are going to discuss the topic multiprocessor performance measurement instrumentation. So let us begin. So what is multiprocessor? Multiprocessor is a system is an interconnection of two or more CPUs with memory and input equipment. The components that form multiprocessor are CPU IOPS connected to input-output devices and memory units that may be partitioned into a number of separate modules. Multiprocessors are classified as multiple instruction stream, multiple data stream. Why choose a multiprocessor? A single CPU can only go so fast. Use more than one CPU to improve the performance. Multiple users can use multiple application, multitasking within an application, and responsive throughout shares hardware between CPUs. What do the difference between multiprocessor and multi-computer? Multiprocessor system is simply a computer that has more than CPU on its motherboard. Multiprocessing is the use of two or more CPUs with a single computer. And multi-computer is a computer made up of several computers. The term generally refers to an architecture in which each processor has its own memory rather than multiple processors with a shared memory. How multiprocessors are classified? So basically, multiprocessors are classified into two types: tightly coupled multiprocessor and loosely coupled multiprocessor. A tightly coupled multiprocessor is a processor in which system have two or more processing units, each shared main memory and peripherals in order to simultaneously process program. Tightly coupled multiprocessor is also known as shared memory system. Loosely coupled multiprocessor systems are based on multiple standalone single or dual processor commodity computers interconnected via high-speed communication system. Loosely coupled multiprocessor is also known as distributed memory, example Unix before cluster. So the difference between tightly and loosely is that tightly coupled system physically smaller and loosely coupled system it's more expensive. And loosely coupled is just an opposite of tightly coupled system, less expensive. Interconnection structure. The physical form from establishing an interconnection network time shares common bus, multi-port memory, crossbar switch, multi-stage switching network, hypercube systems. So time shared common bus. A system common bus multiprocessor system consists of a number of processors connected through part to a memory. Memory unit CPU1, CPU2, CPU3, IOPs and IOP2. So crossbar switch. The crossbar switch organizers consist of a number of cross points that are placed at interconnections between processor bus and memory module paths. Multi-stage switching network. In this network, the basic components of a multi-stage network is two input, two output, and interchange. Hypercube interconnection. The hypercube or binary and cube multiprocessor structure is loosely coupled system composed of n is equal to 2 to the power of n processor interconnected in a n-dimensional binary cube. Hypercube structure for n is equal to 1, 2, 3. This is 1 cube, this is 2 cube and 3 cube. Performance measurements. So the complexity of allocating and scheduling a parallel resource process in which it occurs, not the other process. This generates synchronization and makes it difficult for multiprocessionals of their machines. Multiprocessor users need convenient, affordable mix tweaking and communication delay between various processes in the measured program that don't occur in the non-measured program. Although the amount of SOAR users to achieve the performance, the hybrid measurement system CERT system is evaluated the performance of the algorithm and the stochastic execution time due to directly to maybe our measurement can be esteemed from each programming architecture. To be visual, the measurement system must be a part of a normal implemented as VLSI chips. They introduce sets. The delay caused by the revised interaction of these processes are far less predictable. Even more indigenous is the environment and must not interfere with the system operation or other users. Measurements must be provided for the entire performance hierarchy, starting with the execution time. Often users program includes arbitrary parts of it down through the operations of the architecture hardware. Measurements approach. So measurement is accomplished in two operations: triggering and sampling. Triggering is a detection of the predefined event during program execution that causes trigger sampling of measurements data. And sampling is the collection and storage of a set of measurement data describing computer operation at and between events. The sample may be event trace data or resource utilization data. Event trace data describes the operations of the executing software. Software and hybrid techniques used either interrupt or imbibe code for triggering, while hardware method passively monitors a set of signals, triggering on a specific combinations of signals. Software and hybrid techniques are intrusive since additional code is executed either in the major program or the operating system. This affects the timing characteristics of the major program. So the first figure shows the centralized global access measurements node in which there is an interconnection network and which is connected to a measuring node which encounters time counter, data capture and data storage. And in the figure 2, there is a measurement node connected to a CPU and bypassing the memory management unit and cache. So this is how we measurements and done in the processor. This is a CPU is connected to a measurement node through cache memory to the memory. The figure 3 shows the measurement nodes with distributed data capture and centralized data storage. Next, hybrid VLSI measurement tool. A single measurement node configured from a VLSI chipset can be used for centralized data collection in a tightly coupled system, or the same VLSI chip type can be used in measurement node associated with each processor in a loosely coupled multi-computer. A single measurement node contains one PTRAM and any number of PRAM chips, as shown in figure 8. We'll see. Both the PTRAM and PRAM VLSI chips contains three largely independent sessions. A single measurement node configured from the VLSI chip can be centralized data collection in a tightly coupled system or a same VLSI chip type and can be used in measurement nodes associated with each processor in a loosely coupled multi-computer. A single measurement node contains one PTRAM and any number of PRAM chips. Both the PTRAM and PRAM VLSI chips contains three largely independent sessions, which is data capture, which takes measurement sample when activated via memory with trigger from the program being measured. Data capture is a wiring chip. It controls by the PTRAM chip. Output which places sample are dedicated collection of network on which be read by a local processor or direct memory access controller. FIFO which buffers bursty sample for transmission by the output section. So YTRAM data capture. The PTRAM is intended to operate with a number of different processor interface protocol 80 into 86, 680 into 0, 32 into 32. Only few external bus interface components are needed for partial address decoding in a single section. FRAM data capture section. We have determined that ratio and some short-term average can are an important class of resource utilization measurements. Thus, the PTRAM chip contains two ratio counter pairs and requires an input signal for each counter of each pair. The set of processor signals we want to measure may exceed the number of PTRAM counter, so external gates to conveniently select the desired signal from the set may be very useful. So this is a block diagram of measurement tool in which we have UTRAM and PTRAM. Processor to be measured is this using the chip. With this, I would like to conclude my topic. Hope you liked it.